Hello everyone. So, welcome to the third lecture of this module. So, in this lecture we will learn a method for computing eigenvalues, and here the method will be a numerical methods, because so far you learn how to calculate eigenvalues from as a root of characteristic polynomial. So, here what we will do, we will apply some sort of similarity transformations on the given matrix such that after a sequence of similarity transformations the matrix convert into a diagonal matrix, and from the diagonal matrix we can see the eigenvalues directly as the diagonal elements. Furthermore, the sequence will also contain the information about the eigenvectors of the matrix. So, this method is called Jacobi method, and this method gives a guarantee for finding the eigenvalues of real symmetric matrices as well as eigenvectors for the real symmetric matrix. So, as I told you, it is based on the sequence of similarity transformations, and those transformations will be based on the rotation matrices or given rotations. We will apply the rotation matrices in terms of similarity transformations to the given matrix in such a way that all the off diagonal elements become 0 after a series of transformations. Here off diagonal elements become 0 means there should not be any change in the eigenvalue of the matrix, and that is why I am telling you the similarity transformations, because the two similar matrices will be having the same spectrum. So, first of all, here we should know, or we should have the idea about a rotation matrix. So, what we mean by a rotation matrix? So, a 2 by 2 rotation matrix in a plane is given by this particular matrix. So, it is an orthogonal matrix, you can check, it is having determinant as 1, A transpose will be equal to A inverse and so on. This is about the rotation in a plane by an angle theta. If I talk about the rotation in the space, then first of all we should decide where I want to make the rotation, whether the rotation about x axis or y axis or z axis. The second thing, by which angle. So, if I want to make a rotation about x axis by an angle phi 1, then the rotation matrix will be 1 0 0 0 cos phi sin phi 0 minus sin phi cos phi. If I want to make the rotation about y axis by an angle phi 2, so it will become so the rotation matrix will be this one. And if I want to make it about z axis by an angle, so I want to make it about z axis by an angle phi 3, then the rotation matrix will become, the third column will become 0 0 1, third row will become 0 0 1, and here rotation will be cos phi sin phi 3 cos phi 3 minus sin phi 3 and cos phi 3. So, these are some examples of rotation matrix in 2D and 3D space, 2D plane and 3D space. But suppose a n by n matrix is given to us, then a n by n rotation matrix, let us denote it by j p q theta. So, here we want to put the cos and sin terms in pth rows and qth row, pth column and qth column, and this will be of the form this one. So, except these two rows, rest of row will be like 1 0 0 0 0 1 0 0 like that. In these two rows we will be having the terms of cos theta and sin theta. Like here in pth row I am having 0 0 0, then at the diagonal of pth row and pth column it will be cos theta. At the intersection of pth row with qth column it will be sin theta. Similarly, at the intersection of qth row with pth column will be minus sin theta, and the intersection of qth row with qth column will be having term cos theta. So, let us denote this cos theta by C and sin theta by S. Then the matrix J P Q theta is known as Jacobi rotation matrix or given rotation matrix. The matrix J P Q theta is applied to symmetric matrix A as a similarity transformation, and once we apply it to A, this will rotate row and columns P and Q of A through an angle theta, so that P Q and Q P entries become 0. So, these are two of diagonal entries P Q and Q P, and these two entries will become 0. And I told you this method is applicable only for symmetric matrices. So, hence P Q will be Q P. So, let us denote this the similarity transformation like this. We are having pre-multiplication of J transpose and a post multiplication of J with matrix A, and I am getting my next matrix A dash. So, A dash is J transpose A into J, where J is a rotation matrix with row P and Q and by an angle theta. So, let op A and op A dash be the square root of sum of squares of all of diagonal elements of A and A dash respectively. Then op A square will be Frobenius norm of A minus square of the Frobenius norm minus I equals to 1 to n ai square. So, what we are doing? We are taking square of all the elements and we are subtracting the diagonal elements. Since the Frobenius norm is invariant under orthogonal transformations and only P and Q columns are reformed in matrix A dash, so we can have the sum of squares of diagonal elements of matrix A dash equals to square of the Frobenius norm of A dash minus square of the diagonal elements of A dash. This equals to square of the Frobenius norm of A minus I not equals to P Q A dash I square, because there will be change only in P and Q elements, Pth row P Q and Q P elements, minus A dash P P square plus A dash Q Q square. This will become this particular term, and finally it comes out that the sum of the squares of diagonal elements of A dash will be less than sum of square of diagonal elements of A. It means the square elements are the elements from of diagonal are eliminating, going towards 0, and this is the basic motivation for the Jacobi method. So, here it shows that the size of diagonal part decreases by applying Jacobi transformation. The post multiplication of A by J1 yields change in columns P and Q. In the same way, the pre multiplication of A by J1 transpose brings changes in rows P and Q. Hence, the transformation A dash equals to J1 transpose A J1 alters only rows P and Q and columns P and Q of A, and there is no change in rest of the rows and columns. if we see this transformation in a n by n setup, so what will be the relation between matrix A and A dash? So, the elements A dash Jk of the matrix A dash are given by the formula. So, when J not equals to P and J not equals to Q, A dash Jp will be C times AJP. Please note that here C is cos theta minus S AJQ. Similarly, A dash JQ is given by S AJP plus C AJQ when J not equals to P and J not equals to Q. The diagonal entry in the pth row is given by A dash PP equals to C square APP plus S square AQQ minus 2 CS APQ. Similarly, the diagonal entry in the qth row is given by S square APP plus C square AQQ plus twice of C into S into APQ. The elements on the intersection of pth row and qth column or qth row and pth column is given by, that is A dash PQ C square minus S square APQ plus CS APP minus AQQ. And please here note that the last and rest of the elements we can find by the symmetry, but here please note that this element, this is the off diagonal element in the pth row and qth column or qth row and pth column, and we want to make them 0. So, if I make them 0, I can write 0 equals to C square minus S square APQ plus CS APP minus AQQ, like this given by equation 2. Moreover, the goal at every step of Jacobi iteration is to make the off diagonal elements A dash PQ and A dash QP 0. So, from this we can have phi equals to cos 2 theta C square minus S square. So, it will be cos 2 theta minus twice of cos theta into sin theta, that is sin 2 theta. So, this is phi. Now, from equation 1 and 2 I can write C square minus S square upon CS equals to AQQ minus APP upon APQ. So, from here I can write phi equals to, instead of this I can write this term. So, AQQ minus APP upon twice of APQ. So, this is equals to cot of 2 theta. So, tan of 2 theta will become this value 2i's APQ upon AQQ minus APP, and theta will become 1 by 2 into tan inverse twice APQ upon, in the denominator we will be having AQQ minus APP. However, a less round off error is generated if we use tan theta in computations, like let us assume t equals to tan theta, which is sin theta upon cos theta. So, from equation 1, that is my equation 1. So, if I divide the numerator and denominator by c square, so it will become 1 minus s square upon c square upon twice of s upon c. So, 1 minus t square upon 2t, because s upon c is t, and this gives a quadratic equation t square plus 2t phi minus 1 equals to 0. The roots of this quadratic equation is given by minus phi plus minus square root of phi square plus 1, and that will be signum of phi upon absolute value of phi plus square root of phi square plus 1. Here signum of phi is 1 when phi is non-negative, and it is minus 1 when phi is a negative number. Thus, once we get t, we can calculate c and s by this formula. C will be 1 upon square root of t square plus 1, and s will be c times t. Let us take an example of this method. Consider the matrix this. So, this is a 3 by 3 matrix having elements 1 square root 2 2, root 2 3 root 2, 2 root 2 1, and let us solve this matrix, or let us apply. So, let us take a 3 by 3 matrix and find out the eigenvalue of this matrix as well as eigenvector using Jacobi method. So, matrix is 1 square root 2 2 square root 2 3 square root 2 2 root 2 and finally 1. So, it is a real symmetric matrix. Now, first of all, in Jacobi method we will look for the off diagonal element having the maximum absolute value, because we will perform a similarity transformation to make it 0. So, if I look at the off diagonal elements, the biggest off diagonal elements is this one, that is A31 equals to A13 equals to 2. It means my P is 1 Q is 3. So, it means APP is 1, AQQ is 1, and APQ equals to AQP equals to 2. So, here if I calculate theta, theta will be 1 by 2 tan inverse twice of APQ upon AQQ minus APP, and it is coming out pi by 4, because here it will be 0 in the denominator. So, tan inverse infinity, and so it will be pi by 2 into 1 by 2, it will become pi by 4. This is one of the way of calculating theta. We can calculate it using the t, that quadratic equation, first by calculating phi, then t, and from t we will directly calculate cos theta and sin theta, as I told you. Basically that is more accurate compared to this one. Now, so define matrix J. So, J will be cos pi by 4, that is 1 by root 2, 0, that is cos pi by 4 minus sin pi by 4, sin pi by 4 and cos pi by 4. This is J1. Calculate A1, that is J1 transpose A into J1, and it comes out 3, 2, 0, 2, 3, 0, and finally 0, 0, minus 1. So, please compare A and A1. Just see these two elements. I have made these two elements 0, okay, just by applying this Jacobi rotation. Now, to make this particular matrix as a diagonal matrix, what I need to do? I need to make these two elements are also 0. So, for making these two elements 0, again I will do that. So, my P is 1 and Q is 2, and A12 equals to A21 equals to 2, that is APQ equals to AQP equals to 2. APP equals to AQQ equals to 3, these two diagonal elements. Again if I calculate theta, theta again will be 1 by 2 into tan inverse twice of APQ, that is 4 upon 0. So, it is coming again pi by 4, and my next matrix will become J2. So, J2 will become 1 by root 2 minus 1 by root 2 0, 1 by root 2, 1 by root 2 0, 0 0 1. If I apply again this particular similarity transformation on A1, the matrix obtained in this one, I got the matrix A3, A3 will be 5 0 0 0 1 0 and 0 0 minus 1. So, please look at A3, A3 is a diagonal matrix and hence the eigenvalue of A3 is 5 1 minus 1, and so these are the eigenvalues of A, because I obtained A3 just by applying the two similarity transformations on A. Now, the eigenvector of this matrix A is given by the product of J1 into J2, and I will tell you why I am writing. So, eigenvectors will be columns of this matrix, that is J1 into J2. So, I got the eigenvalue, I got the eigenvectors, and hence I will be able to solve this particular problem for finding eigenvalues and eigenvectors using Jacobi method. Now, actually what is happening, let me tell you few things about this method. Let me write A2 here, which I obtained just by applying J1 transpose A J1 on A. So, it was something like 3 2 0 2 3 0 0 0 minus 1. So, from here I came here and from here I came here. Now, if you remember previous lecture, there we talk about Gauss-Gaussian theorem. So, let us see how eigenvalues are changing or Gauss-Gaussian circles are changing in different iterations of Jacobi method. So, if I talk about this, in this first disk is having center at 1 and radius is 2 plus root 2. So, something 3.4. So, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. So, this will be the disk from the first row. From the second row, center at 3 and radius is 2 times root 2. So, it will be something radius at 3. So, 1 2 3 and center at 2 times root 2. So, something 2.8. So, it will be like this. And the third row is again center at 1, radius is 2 plus root 2, that will be just your first disk. And as I told you, eigenvalues are 5 1 minus 1. So, one of the eigenvalue will be here at 5, one will be here 1, another one at minus 1. So, Gauss-Goren theorem holds for this matrix. However, here what I am having, one of the eigenvalue is the common area of two discs. The Gauss-Goren discs are not disjoint here. If I see in this matrix, so let us say 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. So, first is lambda minus 3, so center at 3 and radius is 2. So, this one, so 1, 3, 4, 5. Second is giving center at 3, radius 2, which is similar to first one, and the third one is having at center at minus 1 and radius is 0. So, in the second matrix which I got in the first iteration of Jacobi method, what is having, the two discs are overlapping each other and one is disjoint. Now, see the third matrix, that is A3. Here simply I am having one of the eigenvalue is here at 5, another one at 1 and the third one at minus 1, and these are the Gauss-Goren disc for the given problem. So, basically what I am doing, by applying the Jacobi rotations to the given matrix, I am reducing the size of Gauss-Goren disc in such a way they become disjoint or they shrunk to a single point, that is your diagonal matrix we are getting here. Another thing I want to tell you here, why I am saying that the product of J1, J2 like that will give me the eigenvectors. What is happening? Let us say A1 is the eigenvalue matrix which is having diagonal entries as the eigenvalue, and this I am getting just by applying a Jacobi rotation on J. Now, as you know that J is an orthogonal matrix, it is a rotation matrix. So, J transpose will be equals to J inverse. So, what happens if I multiply both sides? So, it will become I can write like this, or this is identity. So, A into let us say x1, x2, xn are the eigenvectors of A, and as I told you they will be the columns of matrix J. So, I have written like x1 is the first column of J, x2 is the second column of J, xn is the third column of J. Now, look here, what are these? A1 is a diagonal matrix having the eigenvalues of A. So, it will be something lambda 1, lambda 2, lambda n, this matrix into again J. So, J is x1, x2, xn. So, when I multiply this with first column, what I will get? Ax1 equals to lambda 1 x1, which is the first eigenvalue and corresponding eigenvector for A. From the Ax2 will be lambda 2 x2, Axn will become lambda n xn. So, hence this matrix J is having eigenvectors of A as its column, which I claimed earlier, that you can see from here. So, in this lecture we have learned a method for calculating eigenvalues and eigenvectors just by using the similarity transformations or a sequence of a series of transformations, and those transformations are formed just using the rotation matrices in such a way that the off diagonal elements become 0 In the next lecture we will learn another method for finding the largest eigenvalue and its corresponding eigenvector for a given matrix, and that particular method is called power method. So, thank you very much for this lecture. Bye. See you in the next lecture.